Because here, this is going to pass through the glass and then go down. Then here, with the very same line that has no difference, it doesn't have a dotted line, there's no difference in the line. We are now saying that this ball is now going up. How do we tell that?
Then just go
That's my question, because if it's like that, wouldn't there be a difference that, okay, this one is now dotted and the other one is straight?
And then they would have the same.
This is a bounce.
They should have the same velocity as well, and it doesn't.
You see, then the velocity also, if that was a bounce,
Alright.
it would
Okay, let's reserve this question for
Plus time,
yeah,
okay.
so that we can explain it to everyone.
Like in a
It's a very interesting question, and I must say, you know how it was answered. Hey, I could see.
Then it didn't.
As well as you had a fact, all of you, well, not all of you, but most of you saw 2 bounces, right?
I saw 2 bounces and then I saw 1, and then I was like, I don't have time to fix this.
Sure. Okay.
Actually, would have been cool if you explained on the thingy. Let's do it while we live.
You think we can?
Yeah.
Okay.
So bring the board. Should I bring the board or you go there?
Yeah, Marinki has that.
Oh, Laba.
Yeah, but we'll find it. We'll find it.
We are live.
Oh my. Can you please tell the people that we are... I think we omitted Ubachela to... that we are delayed by 15 minutes. Can I place this a little bit lower? Is that fine? Okay, let's go. Right, good morning everybody. Good morning. Good morning to those of you that are joining us from our YouTube community. It's really been a while since we met like this because we've been going through prelims, and I'm sure most of you, that's if you are a full-time high scholar, you would have gone through our prelims, and I hope that they went well. It would be nice to hear from your comments how that went. But if you are upgrading, then it means that you are preparing towards your final exams, and that's exactly what we are doing. And so even our approach this morning is going to be exactly that, right? We are going to be looking at a couple of questions that we looked at for our own prelim internally, right? So we will see if we can be able to share those with you. Okay, so I'm just trying to make sure that I have this on here. I forgot to tell you what we were starting at 10:15, right? Did I?
Yes, sir.
Askis. All right. Okay, so this thing is a little bit delayed. I'm not sure if it's on my side, but it looks a little bit skewish, Nyana. Oh, so you can't, okay. Oh, okay. Okay, askis, man. It looked a little bit skewish, Nyana. Okay. Do I need to get closer? Okay, good. Okay, awesome. All right. Right, so we're going to look at the questionnaire VPM. I'm going to share my screen here with the people that are joining us from our class. Right. So, Siteni Sizope VPM, and we said we're looking at which other question? Question? Question 3. 8. Question 8. Question 4. Oh yes. Yeah, that's the one I said you guys absolutely sucked at. If that's okay for me to use. All right, now, sure, I do seem a little bit dark, La Piano, but it is what it is. Okay, right, so let's go through this question. And I really do think that with a better understanding of VPM, right, we would be able to answer questions much better. So let's go for it. Okay, and for those of you that are online, please let me know if you've got any questions. Right, so they say to us the velocity time sketch graph for a ball of mass, which is 160 grams. Now please note, if we need to use that mass there, remember that we will need to convert it to kilograms, right? And we do that by dividing it by 1,000. So that would be 0.16. They say it's thrown vertically upwards with a velocity of 6 meters per second, right, from a certain height above the ground, which is shown below, right? They say on the way down, the ball crashes through a thin horizontal glass pane. Niyayibona le nto, ne? Right. Thin okay, I'm emphasizing stuff. I'm emphasizing stuff because we had an argument a little bit earlier on about the practicality of this question. So it is possible. Let's say if it was it was a golf ball. A golf ball is very hard, right? So if it hits a glass surface, it is unlikely, especially a thin glass surface, it's unlikely to bounce, right? But what's going to happen to it? It's actually going to go to, it's going to be slowed down by the glass, but still continuing in the same direction. Does that make sense? Mm-hmm. It's good? Kiangat is not make sure. It's not make sure, ne? Okay. I hit a glass surface, right? I'm going down. It's a hard ball, right? So what happens? It hits the glass surface. It will not go up, right? As it hits the glass surface, well, what happens? It's slowed down, okay? So its velocity will be reduced, but it will still continue going on its way down. Okay, think about in the movies. Okay, I'll be with you just now. Think about in the movies. When a car collides into a glass window pane or something like that, what usually happens, right? It will go through, isn't it? But obviously because of, laws of physics, some of that momentum will be taken away, isn't it? So the velocity will be slightly less. Dando, you wanted to say something?
I want to say that you can use an example of and then when it falls down, it will hit the glass, don't stop, but
beautiful, beautiful,
continue forward.
beautiful. So Undano is making an example with a brick. So if I had a brick, right, and it goes through a glass pane, it's not going to bounce. I think what was the issue, maybe because this was a ball and you expect that because it's a ball it will bounce? Could that be the issue? Was it? Okay, maybe let's not focus too much on the practical elements of it, né? And rather focus on the question itself. Is that okay? All right. Okay, let's try again. So they say to us on the graph, on the way down rather, the ball crashes through a thin horizontal glass pane and then continues downwards, eventually bouncing on the ground. Ignore the effects of air friction. Now this is important because it tells us we are now going into vertical projectile motion. You want to say something, Shez? Yes. Ikebulie light. Yo, Angaz, yes.
Okay, you are dark.
Yeah, yeah, I can see now what it's not working. We move forward a little bit.
Yeah.
Okay. Commercial break. Can you start a song? Okay, let's do this. Okay, let's just move in a little bit. Is it? Okay. All right. But it's not gonna matter kakhulu. Yeah. All right. Still okay. Right. Paul Hello and Scoop Spy. Hey, my daughter. Hey, okay, Scoop Spy. It sounds very cheesy. Okay, right. So they said ignore all the effects of air friction and then assume that none of the broken pieces of glass stick to the ball. Okay? Right. So let's go for it. So I want you guys, as we are going to look at this, I want us to try and interpret what's happening in the picture. Right? So we're going to translate this into some kind of a picture. So first of all, they have taken upwards as positive. How do I know this? Can anyone tell me? How do I know that we've considered upwards as our positive direction here? Say? The direction of velocity, the initial velocity. Right. So you look at this. First of all, what did they say? They said we are throwing this ball vertically upwards. What's your initial velocity? Positive 6. Upwards, positive 6. So it means that they've taken up as positive. Does that make sense? But another way that you can tell if it is positive or negative is the gradient of the graph. Now, I once said to you, please remember, the gradient of the graph is it shows us acceleration. Okay? So if our acceleration is negative, Gonya, what is the acceleration due to gravity? It's 9.8 meters per second squared. In which direction, guys? It's always going to be downwards. It doesn't matter on the whether you throw the ball upwards or or whether it's on its motion down. Remember that gravity never changes direction. Okay, gravity always acts vertically downwards. School is nice. Okay, right. Offense, you still look very suspicious today. Huh? Okay. Are you better in terms of energy? A little bit. Okay. Did you drink water? Okay. All right. So, what's going to happen to this ball? The ball went up and it reached the maximum height. So this point B, the velocity is 0 at that point. Are you guys with me? Right. It is the maximum height. So this would be point B. But after that, what happens? Then it changes direction, meaning that it is now going down. Are you guys with me now? Right. Now, when I look at this, the ball doesn't reach its original point, the point of throw. Why? How do I know that? How do I know that it didn't? Remember, I said to you, once we move from a certain position, if we come back to the same position, then the two speeds should be the same. So if I'm at 6 meters per second, and I come back to the same position, I will get to that position at 6 meters per second. Does that make sense? But what do we notice here? It didn't even get to 6 meters per second. It now got to 3.2. So which means point C must be above the point that we started at. Does that make sense, no? Right. So this is when we now have the thin glass. There's our thin glass. And what happens? The ball breaks through the thin glass. It's slowed down. So it had a velocity before. So just before it went through the glass, its velocity was 3.2 meters per second. And after it has collided with the glass, its velocity immediately after is 0.5, still in the same direction. And which direction is that? Downwards. Why did it lose velocity, by the way? Which principle of physics would this be? Newton's who? Newton? Yeah, Newton could be applicable here. I totally agree, because it accelerated, right? It experienced a force upwards, and that force caused the velocity to slow down. Does that make sense? Right? But which other law can I use? Isho? Momentum. Yes, absolutely. So what type of a collision would this have been? It would have been an inelastic collision as well, no? Right? So that's 3.2, and then immediately after, its velocity becomes 0.5. But remember, it was already on its way downwards, right? So it starts at 0.5, goes all the way down to the ground, and it reaches the ground at a velocity of 5 meters per second. So this is D. When it gets to the ground, when it lands on the ground. But what happens after then? Bounces. But it leaves the ground again, guys. E is when it leaves, no, not E rather. This point here is when it leaves the ground. Do you see? So it got to the ground at 5 meters per second, changed direction, right? Now it is leaving the ground with some unknown velocity, but it gets to maximum height. And this is point E. I hope this makes sense, guys. See sharp, no? Tando is not make sure. Yes. Okay. Lorraine.
No, I hear
Okay, you hear me. Okay, Ngovile? Yes, Ola. Okay, Ugutula? Is it fine? Okay, so which part do you still have a problem with?
No, I can see what I did wrong now.
Okay.
Yeah.
All right. Okay. Right. Now I want us to go through what happened in the question. Anyone from those of us that are online, do you have a question? Do you guys have a question? Okay. Right. Let's look at the first question. They say write down the magnitude and direction of the acceleration of the ball when it reached position B as indicated on the graph. Okay. What would be the acceleration? 9.8 meters per second squared. In which direction? Downwards. Please remember, guys, even when it is stationary, right? On any of the part where the ball is moving, right? We know in this case that we are going to have a downward acceleration, whether the ball is moving up or going down. So, now they ask us the question, how many times did the ball bounce on the ground? Once. Got it? According to the graph, which direction, downwards or upwards, is taken as the positive direction? Definitely upwards, né? Okay, because we threw the ball upwards and that upward velocity is positive. You've got your hand up?
So I wanted to know, so let's say we had let's forget about that last
Yeah, that last thing.
So can you please go up?
Okay.
So let's say from that point, -3.2, all the way to C,
Yeah.
what would, and then let's say we had a dotted line from that point all the way to C, what would that mean?
If we had a dotted line. So sometimes, okay, sorry, I'm just going off tangent a little bit, né? So let's say, for instance, we didn't have that last situation, and that's a very good question. So we would have ended up with a graph that looks like this. All right. No, sorry. Gonja, we threw it up, né? Yeah, we threw the ball upwards, and then it got to 0. Okay, maybe let's do this. Let's assume that this was from, the top of a building. Throw this up, gets to maximum height, and it goes all the way down, right? And then it bounces from the ground. So, threw it at 6 meters per second, and then it gets to maximum height where the velocity is 0. This is over there, right? Now, it goes all the way to the ground. Now, of course, do you see Guti, this part which is below is a bit longer than the top part. So what does it suggest to you? Somewhere along the way, we passed that point, -6. When it is -6, this is when it passes the exact spot where the ball started from. Okay? But because we passed that point, we are going to go all the way down. I'm just sucking a value. Né? Let's say we get to a velocity of -7. Ute -7. Okay, let's say -7. Makes sense? But in this case, remember, this is the velocity with which the ball lands on the ground. But there's like very quick action that's taking place on the ground, right? What happens? It lands and then leaves, right? Almost instantly. So sometimes what the examiner may do is that they may take the time that the ball is in contact with the ground as negligible. Are you with me now? So in that case, if they take the time as negligible, then they will draw something to this effect. Okay, what are they trying to say? That the time that the ball is in contact with the ground is taken as 0. Okay, so almost the ball just bounced instantly, and then it changed velocity. So maybe let's say from 7, now it's going to become 4. So, Lorraine, just for you to understand. So meaning the 7 and the 4 take place, all of it, at the same place. This is in the ground. Despite the fact that on your velocity time graph, it looks like, those are two different positions or two different spots. So this is when it lands on the ground. I'll be with you, Ngobilena. Right? This is when it leaves the ground. Do you see? Right? Now I'm going to show you what would happen if we don't take... It is burning in here. So this is when we take the time with the ground, in contact with the ground, as negligible. And by the way, they are not obliged to use a dotted line. They can even use a solid line for this. right? You just need to know, in my velocity time graph, when this happens, then I know this is when I'm landing on the graph, on the ground rather, this is when I'm leaving the ground. And then what happens? We said then it goes to maximum height. So there it is. We land, we leave. But do you see this is exactly the same spot, right? Land and leave, right? And then what happens? We go to maximum height and we get to that velocity, which is 0. So there it is over there. Does it make sense? Right. Notice the gradient here and the gradient here should be the same. And remember, what does the gradient show us? Gravitational acceleration. Okay. See right on it, guys? All right. Beautiful stuff. So
And then, yeah, another thing, and usually ask if you like calculate the maximum height of the bounce, the ball after the bounce.
after the bounce.
Yeah.
So then, if they were asking me to calculate the maximum height of the ball after the bounce, so in that case, what do I know? I know it left the ground with a velocity of 4 meters per second. At maximum height, my velocity is 0, right? And I know gravitational acceleration. Okay. In that case, I've got 3 things, then I can find out what that height is. It's good, it's nice. Awesome. Ngobile? I answered your question. Ay! Meleng your twice. I'm kidding, guys. Okay. Just need to show you how would this graph look like if the examiner did not take the time in contact with the ground as negligible, right? So let's say, sorry, it lands on the ground, and please just note that I'm just thumb sucking values. So let's say it lands on the ground after 3 seconds, right? So what the examiner may do is that they can either just make this slightly tilted, or they can do this. Okay, so that Nizoibona, let me just use a different color. So they can do this. So do you see that there's a bit of a gap? Let's say this is going to now be 3.1. Okay? Do you see? So there's a bit of a gap between when it landed on the ground and when it left the ground. You see? So in that case, how long did it take? How much time did it take in contact with the ground? 0.1. Because it landed at 3, it left at 3.1. So which means the time that it is in contact with the ground was the difference between the two, which is 0.1. Does that make sense, guys? Beautiful stuff. Even if we made it tilted, you'll see that the first point and the next point would be at 2 separate time values as well. So you just take the difference between the two. All right. Lorraine, I've answered your question.
Yes,
Beautiful stuff. Okay. Now, for those of you online, are there any questions? Okay. All right. They said I should show the statement at the top. Okay. Right. Now let's go back to statement said to. So there's our statement. They said the velocity time graph, sketch graph for a ball of mass 160 grams thrown vertically upwards with a velocity of 6 meters per second. So there's our velocity of 6 meters per second. And from a certain height above the ground is shown below, right? And we said on its way down, the ball crashes through a thin horizontal glass pane and continues down, eventually bouncing to the ground. Right, now I want us to quickly look at the next question. This is where a lot of things went south. I think because generally the understanding, understanding the scenario. So they said calculate the distance between the glass pane, the pane of glass, and the initial position of with which the ball was thrown. So what are we looking for? We are looking for the displacement. Now please guys, please listen very carefully. What is the distance between the glass pane? So here's the, here's the initial position. So here's the initial position of the ball. That's where the ball started. Here is the glass pane. I want to find out what is the distance between the two. Does it make sense? Hello? Mm-hmm. Okay. Do you see, Guti, that is not maximum height? Right? Most of you gave me maximum height. So, I am looking at the displacement between from A till point C. Do you agree with me? Right, let's go for it. Or rather, let me say from A till, I don't know what will we call that position there when it landed on the grass, on the glass rather, where the velocity is negative 3.2. So I'm going to take from A till the glass. What is my initial velocity? Positive 6. What's my final velocity? When it landed on the ground, on the glass, what was the velocity at? It was 3.2. Right? Negative 3.2, I completely agree. Why? Because it was going down, right? So minus 3.2. Gravitational acceleration. What was our acceleration? Positive or negative? Negative. It's definitely going to be negative. Why? Because remember, we've chosen, up as positive. Gravitational acceleration always acts downwards, right? So G is minus 9.8. What was the time? We don't know what the time is, né? But we are looking for the displacement. So we can use our equations of motion. We are looking for displacement. We don't have time. Which equation can we use? Right, so VF squared, yeah? I'm going to use the second one. Yes. VF squared, VI squared, plus 2 times G delta Y, right? Nothing wrong for those of you that prefer S, or rather, it's V squared is equal to U squared plus 2AS. Okay, right. So our final velocity, what was it? Minus 3.2. Please remember to put that in brackets when you're squaring it, which is equal to 6 squared. That's 2 times negative 9.8 multiplied by delta Y. And let's do our gymnastics here, guys. Right, so if I take the negative 3.2 all squared minus the 6 squared, in this case I get minus 25.76, which is equal to negative 19.6 delta Y, and we can divide by minus 19.6. Uh? 1.31 meters. And it is above, that's why I'm getting a positive value, right? It's showing me that the position where the glass pane is above the original position where the ball started. Make sense? Right. Nothing wrong, by the way. There are some of you who went through this method, who calculated the position of the ball going up, the displacement rather of the ball going up, and then calculated the position, or rather the displacement of the ball going towards the window pane. You just need to make sure in that case the one is positive, the one is negative. You add them together, that will give you that total displacement. Are we all okay? All right, beautiful stuff. And then, they said draw a rough position time graph. Hey man, goodness, it was rough. Yeah, it was rough, eh? David Lawrence is asking, sorry to interrupt, sir, but okay, I'm trying to see. There's a heart here that's blocking my. Please zoom in to the statement. But just joined. What paper is this? Okay. This paper was from, I think it was Gauteng 2015. Ne? Yeah, it was Gauteng 2015. But we tweaked it a little bit. Gave it a little bit of an upgrade. Yeah. Okay. Right. And then the last question, they said draw a position versus time graph. Okay. Please just remind me, Guti, the position where the ball is when it broke that last pane was 1.31. Ne? Right. Yeah, I did say. Did they say which reference do we take? Yes, take initial position. I think that's where the problem was. Can I show you two ways in which you could draw this graph? Ne? So the one way is if we took the ground as our zero position. Yeah, so meaning your x-axis would represent the ground. So if that were the case, now this is taking the ground, and by the way, this is not the answer to this question. So taking the ground as our zero position, so this is position in meters, and this is time in seconds. So, do you agree with me that the ball would have started above the ground? Right? So, if I took the ground as zero position, let's say the ball starts there. And what happens? The ball goes further away from the ground. Good? Right? This is until maximum height. The ball comes back. I want this to be perfectly clear. The ball comes back, Ahman, but this is where the glass is, right? Now what happens when it lands on the ground, on the glass? It's slowed down, isn't it? Okay, but it's still going down. So you'll draw gets to the ground. Now look at, you can see, Guti, this parabola and that parabola, there's kind of a mismatch between the two, right? Why? Because remember, it was slowed down. It's not continuous motion. Whereas in that question of Buzangayo, Lorraine, where we've just got continuous motion, uninterrupted motion, it would have been a graph that looks like this, just a smooth graph, right? Now it gets to the ground. I said to you the time axes kind of represent the ground. What happens when it gets to the ground? Bounces up and it reaches a maximum height. So this is what your graph would look like. Is nice? Now remember, this is taking the ground as 0 position, as our 0 position. As 0 position. And I want you to note, guys, the beauty about a position time graph is that it kind of tells you vele the picture that you see. Okay, right? Ball went down, interrupted, and it went to the ground, it bounced, and so on. They said rough because we don't know of any other values, right? None of the values we had, even that 1.31, we're not able to use it because it's a difference in position. Okay, but now let's take the point of throw as our 0 position. So how is our graph going to look like with point of throw as 0 position? Do you agree it started at the point vele, right? And it would get to maximum height. Before it gets back, there it is, it's going to be interrupted by the glass over there. Before it returns to the same position where it started from. So one of the marks that you are going to get was if your graph started from 0, that's an automatic mark. Get it? Okay. And then what happens? There's that interruption over there. It passes the point of throw. It goes further down. Goes further down. It bounces. Does it go back to where it was thrown from? No, it doesn't. So which means the second maximum height, or rather the maximum height after that, will not reach the point of throw again. All right, you're welcome, David. You are most welcome. Right. I don't know if you guys are okay with this. Okay. Right. So please consider, even in the future, whenever we are talking about that bouncing ball effect, right, that it might obviously affect what your position time graph looks like. And please don't forget also to label your graph. Very important. Secret, you know? All right. Beautiful. Beautiful. All right. I just want to charge my online people. Sister, say right. All right, so there are many things that we could have asked around this question, especially if we had given you time values, right? But let's leave it here for now, and let's go on to the next question. Yeah, ne? Hey, nangu Mars ahlupha abantu bakithi. Now they say to us, Mars has an average. So this is on Newton's law of universal gravitation. But Mars has an average radius of 3,390 kilometers and has a mass of 6.39 times 10 to the power 23 kilograms, right? Mars has 2 moons, okay? But to state Newton's law of universal gravitation in words, please allow me not to go through this. You should know it. Nah? Okay. Now, they say to us, if the gravitational force between Mars and the moon and one of its moons with a mass of 1.08 times 10 to the power 16 is that, calculate the distance between, and note that they actually highlighted it to you or underlined it so that you could see what is going on, right? So, but you calculate the distance between the center of this moon and the surface of Mars. Right. Why is that relevant? Now Mars. Here is the moon. Okay? Right. So what were we given in this case? We're given the mass of Mars, 6.39. Huh? And the radius, 6.39 times 10 to the power 23 kilograms. Now, we were also given the radius of Mars, 3,390 kilometers. Ne? Keep that in mind. And then they say to us, skating, okay, and the mass, yes, the mass of the moon is at power 16, sorry, kilograms. Right, we are not given the radius, and they gave us the force between the two, the gravitational force between the two. Now, if we remember very well, what does Newton's law of universal gravitation state? Right? Every object in the universe will attract every other object with a force that is directly proportional to the product of their masses, ne? Or you can say directly proportional to their masses and inversely proportional to the square of their distance from where? From their center. Now please, I want you to note, they said calculate the distance from the center of this moon to the surface of Mars. So meaning, when they exert forces on each other, the distance that we consider is from center to center. But Tina Bates calculated which distance? From the center to the surface. Good? All right. And this is where the problem started. No problem. So F is equal to, GM1 M2 divided by D squared, or you can say R squared, right? We know the force, that's 5.71 times 10 to the power 15. Gravitational, or rather, Newton's law of universal gravitation, or rather the gravitational constant. Konjo, what is that? 6.67. That's minus 11. Thank you. Right. Mass of the moon, of Mars rather, 6.39. 1.08, and this is divided by the distance between them. Right? Now, in this case, you could have calculated the distance first, and once you found out the distance, remember that you still need to subtract the radius. Or you can simply say, well, if we assume, let's say distance yakhona sibiza ngokuthi, yes, it's d squared, ne? But 2d squared, which is this red line here, would comprise of r plus, asingathi r, sithini, x plus the radius, So you can say, instead of putting d squared, you can say this is x plus. That's 3,390 kilometers. Remember that we always place distance in terms of meters. So how do I convert from kilometers to meters? You multiply it by 1,000. Okay? So this would have been 3390000. And you square that. Okay. You could have left it in kilometers, by the way, which means all right. Please, can someone please help us with finding the value of d? 5.71 exponent 15. Actually, we could have done 8,978,569. Yo, 0.93. 0.93. Okay. All right. So this is the distance that we would have found. But what do we still need to do? Right? Subtract the radius, isn't it? Right. So you can say x is equal to the distance minus that radius. And so you find that entire thing minus 3,390. .93 minus 3,390,000, and I think you got 5 something, ne?
5,588,000.
5 million? 588,000.
569,90.
Okay. Nothing wrong also if you wanted to say this is 5,588. Welcome to our new member there, Ubani. TikTok complications. Yeah, guys, your synonyms. Right, this is kilometers. So this is what we could have expressed this as in terms of kilometers. Are we all good? Is it right, guys? Yeah, so please be very careful whenever. I think this is the trick that they can introduce to this, right? Where they don't give you the distance from center to center, but they rather give you the distance from maybe radius to center, or sometimes even from circumference, right? Circumference to circumference. So we need to be very careful of that. Questions? Huh?
No, I wanted to know, like, why did you do that as 5,588?
Yeah, divided by 1,000. In fact, that would have been 5,589 kilometers. And it was in meters, so I'm trying to express it in kilometers. Then you could express that in kilometers. And there was nothing wrong. You could have left that in kilometers, by the way, and use, subtract kilometers to kilometers. Nothing wrong with that. Okay, right. Okay, this is for grade 12, for Romeo who's watching, right? Asking what is this for grade 4. But I mean, this is also relevant for grade 11 as well, né? Okay, so grade 11 as well as grade 12. All right, are there any other questions in relation to this? Can I move on? All right, beautiful stuff. Konyanite, what was the next one? 6.5. Okay. Right, let's go for it. That's work, energy, and power. Ne? I want us to, and yes, it didn't go badly at all. Yeah, you guys were able to answer most of the stuff. I think save nje for a few things would go 6.5. I wasn't too concerned, I must admit. So they say to us, a box of mass 86 kilograms is accelerating down. Sorry, I'm trying to. I was going to ask, but then it would mean you'd have to move. Yeah, whatever you do, don't move. Okay, all right. All right. So I wanted for us to look at the scenario together, né? Because there was something quite peculiar with this question. And I think someone asked me this question not too long ago. Oh yes, it was you, Lebune, who was asking me, is it possible for applied force and frictional force to have the same direction? Right? So this is one of those cases. And I want you guys to really, really pay attention to that. So we've got a box of 86 kilograms, which is accelerating down a surface inclined at 25 degrees to the horizontal. They say a man applies a force F upwards, parallel to the plane, in an attempt to prevent the box from sliding down the inclined plane. But what happens? In spite of the man's effort, the box is accelerating down the inclined plane. So what's happening? This person is pulling the box up the incline, but despite the box being pulled, it's still going down. Are you guys with me now? So let's talk about frictional force. What does friction oppose? Yeah. So in this case, if I were to look at a free body diagram of the forces that are acting, and please guys, ningasabi to draw a big dot, right? If there are forces that are in the same direction, please don't put them one on top of the other, or kind of make one line with two arrows. Okay, please rather draw a big dot and show each force individually. Another thing, again, I still found some of you not labeling the diagram fully. Okay, you used acronyms instead. So, what are the forces that are acting? We've got an applied force, ain't it? Applied force. The man is pulling the box. Yes. The second one, normal force, I agree. Remember, normal force is perpendicular to the surface. So there's our normal force over there. So this would be the normal force. What other force do we have? So we've got gravitational force, or the weight, note, vertically downwards. And then finally, I want to talk about the friction in this case. Where is the box sliding to? Downwards. So friction must be acting? Upwards. So it must be acting upwards, parallel to the incline. So, when they ask us to draw a free body diagram, please, I want us to always consider this. If you use acronyms, right? So if you said N for normal force, on the or below your diagram, then say that M stands for normal force. Give the keys to your acronyms. Normal force, if you called frictional force Fk or whatever, then say Fk would be friction and so on, right? Please guys, this is very important for the examiners so that they know exactly which forces are there. Are we all together? Right. Now I know there would be another diagram where you might want to include the components as a gravitational force. Okay. That's still okay, but I think as it is now, the agreement is that they prefer that you draw this type of diagram instead. Okay, not too much of an issue with IEB per se, but definitely DBE could be an issue. Is it right, guys? Okay, question?
In terms of no, we go like this.
So if I were to draw the two components, right? So which means you'd have to get rid of the weight if I wanted to draw the components of gravity. Okay? You'd have the perpendicular component of gravity. You'd have the parallel component of gravity. Okay? What I want you to notice is that the normal force and Fg perpendicular usually just make a straight line to each other. They are skewed in line with the incline, but they make a straight line with each other. Okay? And that's why if they were to ask us here, maybe to calculate the frictional force, right? We would use Fg perpendicular as our normal force, right? Because they are equal essentially. All right, now let's go quickly. They say, what is the non-conservative force? Konje siteni. These are forces whose work done depends on the part taken. Right, so please note that. That would have been a good 2 marks. The coefficient of kinetic friction between the box and the surface is 0.22. Prove that the magnitude of the kinetic friction is 168.04. Now, do you see? This is when we are going to use our normal force. And what do we note? The normal force is equal to the perpendicular component of gravity. Okay, right. So, to calculate friction, we're going to say coefficient multiplied by normal force. That's 0.22. But remember, what is the perpendicular component of gravity? We always say mg, the cos of the angle of elevation, right? Right. So that's 86 times 9.8. The cos of 25. 168.04, which is exactly what they asked us to prove. Guys? Right. Please, and I saw some of you who still used gravitational force. So you said friction is coefficient multiplied by normal force. But when you substituted here, you just left it at 68 times 9.8. Remember, this time, this is not a flat surface, right? So because of that, remember that normal force is now bent, or what can I say? It's now skewed in line with your incline, because the normal force is always perpendicular to the inclined plane. All right, and then the next question, okay, state the work energy theorem in words. I know that you know this, but some of you still said the work done, you just simply said the work done is equal to the change in kinetic energy. What's wrong with that statement? Okay, you're supposed to either say the total work done or the net work done. Okay, please note that. Nah? Right, and then they said draw a labeled a free body diagram. We've already done so, fortunately. All right, and they say the box accelerates parallel to the incline, down the incline for a distance of 0.9. Okay, so what did they give us? Acceleration. All right, man on the box. So what are we looking for? Okay, Amora is asking the question, in which conditions will we be able to use Fy and Fx? So Amora, for you to understand, there's a difference when we are talking about a force, or rather an object on an inclined plane, right? And a force that is acting at an angle. So if I had an object that was being pulled, but they are pulling it at an angle, in that case, let's say we've got force F. So you are going to then resolve your forces into the two dimensions, which is the horizontal as well as the vertical. So this is when we've got an object that is being pulled with a force that is acting at an angle. That's when you'll be able to do so. I hope that answers your question. Right, so let's go to the question that they asked us. Use the work energy to calculate the work done by the man on the box. So, which principle? If I were you, if I were you, I always think by non-conservative forces is the much easier method. But I'm going to show you both. But the problem is that it's not a problem. I mean, we can always. So we don't have a vertical height. Right? What was the distance? Epoxely movie. 0.9. Is it for us to get that height there? It is possible, right? How do we do that? There's our angle, opposite over hypotenuse. Which trig ratio is that? That's sine. So meaning, if I wanted to find out what the height is, the sine of 25 degrees is opposite, which is the height, divided by hypotenuse, which is 0.9, and so the height is 0.9 sine 25. I'm going to leave it in that format. Okay, that is my vertical height. Then I'm going to say, now please, I want you to follow me, guys. The work done by non-conservative forces is equal to the change in kinetic energy plus the change in potential energy. Now let's talk. What's the work done by non-conservative forces? What are non-conservative forces? Right? Ningang definition. I just want the ones. Frictional force, that would be the work by friction, and the work done by the applied force. It's only those two. So which means work done by applied, by work done by friction, that's half times m, that's Vf squared minus Vi squared, plus mg, sisonke it, guys? Right, where's the box going? Down. So, I'm looking for the work done by force F. I just need to make just a slight adjustment. I don't know if it's really from my side or, yeah, just need to make a slight adjustment to my Is it left? You know, right now my mind is playing tricks on me. I'm trying to figure out to cover this a little bit more. Okay, I think I'll try. Maybe.
See from WF. So where WF is.
Yeah, so maybe let me
all the way
make an
to-
adjustment here where I'm writing, yabo? Okay. So we've got work done by the applied force plus the work done by friction. Okay. Now remember we've got 86 kilograms. Right. Now I want you to note in this case, do I have the final kinetic energy or the initial? I don't, ne? So what do I do now? I need to remember. Konye, where is this? Where is this? Oh yes, there we go. Right. So, you remember what they gave me, acceleration. What do I do with that acceleration? Vf squared is equal to Vi squared plus 2 times A delta x. Right? Okay. So if I take Vf squared minus Vi squared, take that to the other side, what am I left with? 2 times acceleration is 1.54, right? Delta x is 0.9. Do you guys agree? So I've got an expression for Vf squared minus Vi squared. What do you note? Isn't that the same thing that I have there in those brackets? I do, right? So this would be 2 times 1.54 times 0.9. All right. And this is where the height came in, right? So that would be 86 times 9.8. And I want you guys to note, what's our final height? Right? I'm assuming that I'm going to get to 0. Okay? So that would be 0. What was my initial height? Where's that height that I calculated? Do you remember that height we calculated there? I need to color from the top, and then it went down. Do you agree? So in that case, it means that that height would have been, what was it? 0.9 sine 25. Right. So that would have been our height. But we are still not done. We're looking for the work done by the applied force. Now let's talk about frictional force. So, work done is force times displacement, the cos of the angle, isn't it? What's our frictional force? We calculated it there. That's 168.04 multiplied by displacement, which is 0.9. Right. What is the angle between the direction of motion and the frictional force? It's 180. So this would be cos of 180. Sorry that I'm squeezing that in there. But you get the point, don't it? Right. All that's left for us to do, guys, is just mathematical gymnastics. Okay? I want to show you just another way in which you could use the work energy theorem. The other one is 86 times 9.8 times. Please note this is negative because it's 0 multiplied by and then I take this to the other side. Please note it's going to be negative, right? Right, and we ended up with a force, or rather the work done by the applied force of 50.13. And please note that is in joules. That's negative, by the way. Okay. Is it right? Our people online. Nessa second.
Yes, sir. Okay.
Okay. Any questions?
Yes, sir.
Yeah, go ahead, Rapula.
So I wanted to ask, I had a confusion when I was looking at this question because they said we had to use the energy principle. So I saw that I'm going to use the equation of motion to get the expression for the changing in velocity.
Yeah.
So I wanted to ask that, like, are we allowed to use, for example, Newton's laws just to get some of the...
Absolutely, Rapul. Mamela, the fact yokuthi basinikeze acceleration left us with no choice, right? You either had to use equations of motion or we could use Newton's laws, and I'm going to show you how to use Newton's laws now, right? And by the way, guys, I want you to also note the fact yokuthi, I don't know if you've noticed that the examiner now kind of likes putting together different sections, right? If you notice, prelims that they were writing now, they kind of did that a lot. Okay, Vele, that's how physics should be done. Okay, so what I'm just trying to say is that you'll find a cross-pollination between different parts of physics, and you shouldn't be afraid to use the one principle. The problem comes, okay? The problem comes when, if they asked you to use a certain principle, and that's the only principle that you use. So for instance, if they said to me, use principles of energy, and I don't use anything related to energy, right? Then that's a problem. Then I use other principles instead. Then that's a problem. I hope that answers you, Rapula.
Thank you, sir.
All right, awesome stuff. Okay, now that ukhuluma Newton's laws, let's quickly look at how we would have been able to answer this question using Newton's laws. So firstly, do you agree with me that F net is equals to MA? Okay? So, we would have said F net is equal to mass times acceleration. Our mass is 86. Our acceleration is 1.54. Right. What do we get there? $132.44, no? I have a feeling some of you will prefer this method over the one that I did now. Right. But what do we note? The net work done is equal to the change in kinetic energy. Angit? Right. Konje, what is net work done? Right? It's the work done by all the forces, isn't it? Okay. Now, I want you guys to note in this case that, again, I would find myself in the same situation where I've got F net multiplied by delta x, the cos of theta. Now I know what my what is F net? C'était 132.44 multiplied, by 0.9. Now I want you to note, Gonja, where was this guy accelerating? Where was it accelerating? In which direction? The object. Down the slope, right? So, of motion as positive. Okay? So meaning my F net was going down the slope as well. So if I'm using, so what would be the angle between direction of motion and F net? It would be 0, right? That should be 0 because they're both in the same direction. And so this will be equal to the change in kinetic energy. All right. But what do I also note in this case? Right, I've just found the change in kinetic energy. I can say that the net work done. Now I'm taking the sum of the works done. Okay, so in this case, if I look at my free body diagram, it would be the applied force. In fact, when I'm talking about the works that are done, remember when I use net work done, I now need to work to also include work done by the parallel component of gravity. Okay, so which means this guy here minus this guy here minus this guy here would give me the net work done. Does that make sense? So net work done by parallel component of gravity plus work done by friction plus the work done by the force F. Sisonke guys? Okay. All right. I think this will be the last thing that we'll be able to cover for today. Sure, there's still quite a bit for us to cover for physics. So I already know what the net work done is. It's that guy, isn't it? That we found out, which is equal to change in kinetic energy. Work done by gravity parallel, that would be Fg parallel, which is mg, the sine of theta. This is just the force, Fg parallel, isn't it? Multiplied by delta x, 0.9. The cos of, it's 0 because it's going down the incline, isn't it? Then you've got work done by friction. We already had found that. That's how we got frictional force 168.04 times 0.9. The cos of, that would be 180. And then we're looking for the work done by F, force F. So I'm going to leave it there. But all of this is equal to what we calculated there, which is 132.44 times 0.9, cos of 0. And then you can do all of your gymnastics mathematically. So you can choose which one. Which one do you think is better? The first or the second? Zonke ziyafana. Okay. None of them are better. Mbona ngathi ufuna nokulahlela isandla. Yeah. To the Adore, or is it Theodore? I don't know how to pronounce. Are these every day? No, we have these once a week, but we will announce. We have these once a week for physics. We have these once a week for maths on Mondays, but I will let you know that at the end of our session. Would it be okay to close it there for today? Oh, it feels like a lot. I see. Agnes? Yeah, well, there were still some other questions that were asked.
Asking that's the last day.
Oh yeah, angithi besifuna F.
Different.
Yini different? It's different kanjani? Yeah? Hey, Nina, must stop smoking that thing. Okay, I see calculate 10, 9 calculate. Times 0.9 cos 0, it's 1. And then this is going to be minus 86 sine 25 times 0.9, yeah, cos 0. And then the other one, remember Gutine cos 180, right? So what I'll do is that I'm going to, let's subtract it, 168.04 times 0.9 cos 180. I get the same answer. Okay. Minus 50.13 newtons. I really do think that there's quite a lot to revisit. So we'll look at the other questions now. I think that brings us to the end, to those of you that are watching us from our online community. Okay? What we will do is that for us, Esilan, let's continue tomorrow. But can I just check just so that we're able to see? Tomorrow sends which question? Question 8. Hey, question 8. Agambanga kahle. 8 point?
Question 8 and question 4.
Okay. Yeah, Doppler effect wasn't so bad. Question 9. Okay, we'll look at the rest. It's fine. So sizokhuluma ngayo afterwards. But maybe let me close this out with saying, so as I did say, to those of you that are joining us from our YouTube community, please do note that we have these sessions on Mondays for maths, on Wednesdays as well. You are more than welcome to be a member in this channel. You'll get a bit more value than just everyday subscribers. But please, for all of the details, you can also check the comments that are there. We'll always try to respond. And thank you to those of you, Ulisiho Mudisane, who's just joined us as a member, to Gunolo Innocentia, thank you for joining us, as well as TikTok Complications. I don't know what that is, but thank you so much. I'll see you guys next time. Shop, shop. Okay. Nabo sebahambili. Doing what they do best. Okay.